In general, whenever there is a charge Q moving with velocity V in a magnetic field B, the force exerted by the field B on the charge Q, the force can be calculated from this equation, QVB sine theta. So from this equation, we may define the magnetic field B as force per unit charge per unit velocity, and also it depends on the angle, sine the angle between V and B. Recall what we learned before when we defined the electric field, force per unit charge, and when we define gravitational field, force per unit mass. So for gravitational fields, the intrinsic quantity of interest is the mass. For electric field, the intrinsic quantity of interest is the charge. For magnetic fields, the intrinsic quantity of interest is a moving charge Q with some velocity V and some angle theta. The unit of the magnetic field in the SI system is Tesla. 1 Tesla is equivalent to 1 Weber per squared meter. When you apply the dimensional analysis, you can see that 1 Tesla is also equivalent to 1 Newton per ampere meter. Before the introduction of the SI system in 1965, another unit was used for the magnetic field, which was named Gauss. 1 Tesla is equal to 10 to the power 4 Gauss. So as you can see here, the magnetic field depends on 4 factors. The magnetic force on a charge depends on 4 factors: the charge, the velocity, the field, and sine the angle between V and B. So the maximum value for this force occurs when theta is 90 degrees. Sine of 90 is 1. Sine of 90 is 1. That is to say, when the direction of motion of the charge is perpendicular to B, then the force is maximum. On the other hand, when the direction of motion is parallel, when V is parallel to B, theta is 0. Sine of 0 is 0, so the force is 0. So this is very important property of magnetic force that we need to take note of. The force is determined not only by the product QVB, but also by sine of the angle. So it depends on the direction of motion for the charge. And as we see here, for the same QVB, depending on the angle, when V is parallel to B, the force is 0. When V is perpendicular to B, sine 90 degrees is 1, so the force is maximum. Usually, we use the right-hand rule to predict the direction of the force. It is common to assign the direction of motion to the 4 fingers. So the 4 fingers will point with the direction of motion V. Then we curl them toward B. So here, if you use your right hand, if you open your right hand, you assign the direction of motion to the direction of the 4 fingers. Then when you curl the 4 fingers toward B, the thumb will point upward. That will be the direction of the magnetic force. You need to check with your right hand to practice so that you will learn this important rule. As you can see here, the direction of the force will always be perpendicular to the direction of V and the direction of B at the same time. Okay, the direction of the magnetic force always makes 90 degrees with both V and B. So here, this is a three-dimensional plot. If V and B is in this horizontal plane, then the force is in the vertical plane. And the direction of F, you apply the right-hand rule, you assign the four fingers to the direction of V, then you bend them toward B, you curl the forefinger toward B, and in that case, the thumb of your right hand will allow you to predict the direction of the magnetic force. This is when the charge is positive. If the charge is negative, all what you need to do is just flip this direction in the opposite direction. So we apply the right-hand rule, assuming the charge is positive. If it is negative, we just flip the result. You flip the direction of the thumb, flip the direction of F. It will be downward if the charge is negative. Okay? So here we see the field is going this way. If the charge is moving up, apply the right-hand rule. If it is positive, this would be the direction of the force, thumb. If it's negative, this would be the direction of the force. You need to practice so that you master the right-hand rule and learn how to apply it. Remember always that force is perpendicular to the plane created by V and B, and it follows the right-hand rule. Usually we assign the direction of motion to the four fingers, and then we curl that toward B. The thumb of the right hand will predict the direction of the force. Example: a proton moves with a speed of 1 × 10⁵ meters per second through Earth's magnetic field, which has a value of 55 microtesla at a particular location. When the proton moves eastward, the magnetic force acting on it is directed straight upward. And when it moves northward, no magnetic force acts on it. So when it moves northward, this means it is parallel to the magnetic field. When it is parallel, the angle is 0. When the angle is 0, there will be no force. So no magnetic force. Then, A, what is the direction of the magnetic field? B, what is the strength of the magnetic force when the proton moves eastward? C, calculate the gravitational force on the proton and compare it with the magnetic force. Compare it also with the electric force if there were an electric field with a magnitude equal to 150 Newton per Coulomb at that location. A common value at Earth's surface, this value. Note that the mass of one proton is 1.67 multiplied by 10⁻27 kilogram. This is a simple application that will allow you to practice to check on the right-hand rule. So point your thumb in the direction of the force and your fingers in the direction of motion, which is eastward in this case. When you curl your fingers toward the magnetic field, the thumb points north, which must therefore be the direction of the magnetic field. The magnitude of the magnetic force can be calculated. F equals QVB sine theta. Q, the charge for one proton, is 1.6 by 10⁻19 Coulomb. The velocity is 1 by 10⁵ meters per second. And B is 55 microtesla. Micro means 10⁻⁶. The angle is 90 degrees. Sine of 90, evaluate. This is 8.8 by 10⁻19 in Newton. Then for gravitational force, F is equal to G. The mass of the proton is 1.67 by 10⁻27 kilogram. and G is 9.8. So the gravitational force is 1.64 by 10 to the minus 26 in Newton. Finally, the electric force is QE. This is Q for 1 proton multiplied by E. The answer is 2.4 by 10 to the minus 17 in newtons. You see that the strongest force is the electric force, followed by the magnetic force, followed by the gravitational force. Gravitational force is much, much weaker than either the electric or magnetic force. A charged particle moves in a straight line through a region of space. It moves in a straight line. Which of the following answers must be true? Assume any other fields are negligible, only the magnetic field. So if the charge moves in a straight line, what do we predict? We have these suggestions. The magnetic field has a magnitude of 0, has a 0 component perpendicular to the particle's velocity, has a 0 component parallel to the particle's velocity. We need to apply the formula, this formula QVB sine theta, to answer this question. So in this case, the right answer, the magnetic field has a 0 component perpendicular to the particle's velocity. 0 component. When that is the case, then the force is 0. When the force is 0, the charged particle will continue moving in a straight line because there is no external force acting on it. Another example, a proton moves at 8 by 10 to the power 6 meter per second along the x-axis. This is the direction of motion for the proton. It enters a region in which there is a magnetic field 2.5 Tesla directed at an angle of 60 degrees with the x-axis. So this is the magnetic field making 60 degrees with the x-axis. Find the initial magnitude and direction of the magnetic force on the proton. Calculate the proton's initial acceleration. As usual, proton mass is 1.67 by 10 to the minus 27 kilogram. We need to apply the right-hand rule. So assign the 4 fingers to the direction of V and curl them toward B. So your thumb will point upward. That would be the direction of the magnetic force. The thumb points upward in the positive Z direction. Then the magnitude of the magnetic force can be calculated, QVB sine theta, Q for the proton 1.6 by 10 to the minus 19 coulombs. V, we are told, is 8 by 10 to the power 6, and B is 2.5 Tesla, and the angle between V and B is 60 degrees, so we need sine 60. Evaluate the answer, it is 2.77 by 10 to the minus 12 in newtons. Now we apply in Newton's second law. This is the net force, it is equal to MA. So now we can calculate the acceleration A from this equation. A, you need to divide the force by the mass. It is 1.66 by 10 to the power 15 meter per second square. So this is the magnitude of the acceleration, this is the magnitude of the force, and this is the direction of the force. The force is perpendicular to the original direction. Always when the force is perpendicular to the direction of the velocity, the resulting acceleration will be perpendicular also, because the acceleration follows the direction of the force, and because of that, the net outcome is to bend the direction of motion such that the charged particle will move in a circular path inside the magnetic field if the magnitude of the velocity is constant.